Welcome to the OSIRIS-REx News Conference. Our event should begin momentarily. Today's conference is being recorded. If you have objections, you may disconnect at this time. If you are also monitoring the event video, please mute the audio on your TV or computer and listen only to audio from the phone. If you'd like to ask a question during the question and answer portion of the briefing, please press star 1 to be added to the queue. If you'd like to withdraw your question, press star 2. Do not use your speakerphone when you are asking your question. Again, today's conference will begin shortly.
Hello and welcome to today's Media Telecon. Today we are discussing the initial findings of NASA's OSIRIS-REx Asteroid Sample after its reveal earlier today. I'm Shaniqua Vereen with NASA's Office of Communications. In the room with me, I have a panel of experts that will answer questions for you today. With me is Nikki Fox, NASA's Associate Administrator for NASA's Science Mission Directorate. I have Jason Dworkin, OSIRIS-REx Project Scientist from NASA's Goddard Space Flight Center. Professor Dante Loretta, OSIRIS-REx's Principal Investigator from the University of Arizona. And Dr. Francis McCubbin, Astro Materials Curator from NASA's Johnson Space Center. We'll begin with some opening words from Dante Loretta, the Principal Investigator, and then we'll open up for questions for media on the line.
Thank you, Shaniqua. It's great to be here at NASA's Johnson Space Center, where since September 25th, when the OSIRIS-REx samples arrived on center, we have been systematically and methodically getting into the science canister and ultimately to the sample collection device, which we call TAG-SAM, the touch-and-go sample acquisition mechanism, the actual piece of spacecraft hardware that touched the surface of asteroid Bennu and collected material back in 2020. It's been a very exciting set of weeks. When we first opened the science canister, we saw that there was abundant fine-grained black asteroid dust, as well as larger particles of about a millimeter or so, roughly a 1/16 of an inch across. We did collect some of that material for distribution to our sample analysis team. We had a group here, the Quick Look team, which took it to the electron microscopes and optical instruments, as well as shipping some of it to the Carnegie Institute in Washington and NASA's Goddard Space Flight Center for initial assessment. And we're already thrilled with the results. We have verified that Bennu is dominated by water-bearing clay minerals. We have found iron minerals in the form of iron sulfides and iron oxides, which themselves are indicative of formation in a water-rich environment. And perhaps most exciting, the sample contains about 4.7% by weight carbon, which is obviously the essential element for all life on Earth and central to our astrobiology investigations. We did remove the TAG-SAM device from its capture ring. You can kind of think of this like a boot clicking into a ski. So we had to remove the cams and lift it off. When we did so, some material slipped out from the mylar flap, which is kind of the check valve designed to hold the material inside the sample collector. And we got some amazing shots of the diversity of particles that are visible right now. Over the next couple weeks, the curation team will continue to disassemble the TAG-SAM. There's a series of steps that we need to go through before we can actually get into the interior, but we're optimistic that we'll have a pretty good estimate of the entire mass of the sample within 2 weeks or so. So it was a really great set of presentations we gave today, and I believe we're here to allow media from all over the world to ask any follow-on questions.
Thank you, Dante. And if you are media on the line, to get on the queue, press *1 to be put into the queue for online questions. I think we do have our first question up for the group, and that is from Marcia Dunn with AP.
Oh, yes. Yes, Dante, I was going to ask you when you plan to open up your container, and you said in 2 weeks. That's great. I saw some of the big rocks, the troublesome ones. Could you say? Can you hear me here? I'm sorry.
Yeah.
Oh, okay. Yeah, I was. Thank you for answering how many weeks before we get some clarity on how much you brought back. 2 weeks. But the rocks that we saw, the troublesome ones especially, looked pretty big. How big were those? And based on the size of those bigger rocks, what's your best guess of how many grams you have based on what you can see?
Well, that's a tricky question, Marcia. So I can definitely tell you about the size of the rocks that we're seeing right now, and maybe Francis will want to weigh in here in terms of the challenges in estimating mass. But yeah, we see some of the troublemakers. There's still rocks that are wedged between the bottom of TAG-SAM and the mylar flap, and as we know, in 2020, we saw particles escaping TAG-SAM as a result. Some of those are 1 centimeter or 2 centimeters in their longest dimensions. And when I look at the entire exposed material, I'm seeing of order a dozen stones at that centimeter or larger scale. But Francis McCubbin's here. He's our astromaterials curator at Johnson Space Center. Maybe you want to talk about the challenges of trying to come up with a mass based on what we know right now.
Right. So the biggest challenge, so we have containerized about close to 1.5 grams of material off of the avionics deck. And as we were measuring those particles, particularly the intermediate-sized particles, some of the larger ones weighed less than we would expect, and some of the smaller ones weighed more than we would expect. And so there's obviously some variations in density for this sample. But what we can say is we're very excited about the volume of material that we have.
Thank you.
Thank you, Marcia. Our next question will come from Alexandra White with Nature magazine.
Hi, yeah, thanks much for holding the follow-up call. I wanted to ask about this 4.7% carbon. How does that compare to other meteorites? There was a mention, I think, of that perhaps being the most highest carbon percentage in extraterrestrial samples. Just walk me through a little bit about kind of what other carbon-rich asteroids contain in terms of percent carbon and how Bennu compares with this 4.7% number, please.
Hi, this is Jason Dworkin, project scientist, NASA Goddard. The 4.7 is on the high end for carbonaceous materials, for meteorites and carbonaceous asteroid sample return, of which there's been one other. It's within the range of what was seen on Hayabusa 2, and this is, again, very, very early results from one set of samples that was collected in the quick look exercise. So there will be a lot more to discover as we explore, but in the range of meteorites that have been studied, this is among the highest. It's in the top tier. It's what we were exactly hoping for, and we are delighted to be able to explore that over the next 2 years and, of course, over the next decades.
Thank you. Our next question is going to come from Kenneth Chang with the New York Times.
Hi, thank you. I I have a question. What is the definition of organic carbon in this context? And how do you differentiate that from non-organic carbon?
So we have a working definition of organic carbon, which would include carbon-containing molecules that you could have graphitic material. We still call that organic. Now, of course, remember that we haven't done analyses of things on these edge cases yet. That'll happen. So to get overly detailed, we would consider, say, Buckminster fullerene, which is pure carbon, could still be considered organic. We would not consider something like a carbon steel to be an organic molecule, even though it has carbon. Typically, organic is defined as carbon plus hydrogen, but we have some other cases of organic compounds that would be edge cases for those. But in general, for general audience, carbon molecules that have carbon, hydrogen, and other atoms.
And they're definitely not in a crystal. With something with a unit cell with a repeating, structure like a carbonate mineral, we would not consider organic. So the molecules are soluble. Some of them can be extracted with water or acids, and some of them are insoluble, but they look like kind of macromolecules, very large in structure.
Coal-like.
Yeah.
And you, of course, can form crystals of organic compounds like the sugar in your sugar bowl, but that's not the sort of thing that we're discussing here.
Right.
All righty, thank you. The next question is going to come from Leo Enright with Irish TV.
Yeah, thanks very much for doing this extraordinary material. I was a bit curious about the clay. You've confirmed, obviously, I mean, you saw it spectroscopically at the asteroid, but you're now confirming clay minerals. And you were talking, Dante, during the Houston briefing about a catalytic element in the metals that you're seeing, all of which really speaks to extraordinarily strongly to the idea of formation of organic compounds and more complex molecules. Could you talk about how this all might fit together?
Sure. So of all the minerals that I introduced, we've got the clay minerals, we've got the iron sulfides and the iron oxides. All of them have been investigated in various prebiotic studies as potential catalysts for important molecules that may then go on to be incorporated into biology at some point. We're interested in the origin of homochirality, which is the property of amino acids to have a left-handed version and a right-handed version, and life preferentially uses the left-handed version. The sugars are opposite. The ribose in RNA, for example, dominantly as a right-handed version. And so when you produce these things through an inorganic chemical reaction, you tend to get both hands in equal abundances. But there are certain properties of these mineral surfaces. I know the iron oxide magnetite has been looked at in this manner, where it might preferentially absorb one-handed molecule over another based on defects in the crystal structure, and that might be a natural way to concentrate one version of the organic molecule over the other. There's also just catalytic properties where we may be able to produce molecules that wouldn't otherwise form rapidly without the mineral surface to speed up the rate of the reaction. And maybe Jason, do you want to add anything to that?
It's a wide range of things that can be considered. The prebiotic chemistry has decades of studies on what could be plausible, and it'll be very exciting to be able to look at the chemical networks that we'll be able to piece together from Bennu, looking at the organic compounds in the interaction with the inorganic and the compounds in the mineral species, to try and push those frontiers forward and look at some old hypotheses to see if they may have played a role on Bennu's parent body.
I had a follow-up, if that's possible.
Yep, go ahead.
Oh, thanks. Yeah, I was curious also about the water content of these samples. Are you expecting to see H2O? And if so, we heard again at the Houston briefing earlier about, we know that, water may have come to the Earth from objects like this. But I do recall that the Europeans were surprised to find that the D to H ratio at the comets was not consistent with that. Is it possible for you to progress this discussion?
Yes, absolutely. So we will be looking for water, and really, to be specific, it's the hydroxyl ion, the OH ion, which gets incorporated into the crystal structure of the clay minerals. You can have interstitial water molecules in between the layers of the clays as well, and we'll be looking for both of those forms of water. And we will absolutely be measuring the deuterium to hydrogen ratio of the minerals and any other phases. One of the things we're excited to look for are fluid inclusions, the carbonates and the sulfides in particular. If they formed by precipitation in a hydrothermal system, they may actually have trapped some of the water, now kind of like locked inside a little cell inside the mineral itself. And so we might actually have samples of the asteroidal water directly. That's still a hope. We need to do the work, but it's not out of the realm of possibility. So yeah, all of these questions, the isotope ratios, the form of water, where it is in the crystal structure, and unraveling the formation pathway is part of our sample analysis plan.
And following that deuterium to hydrogen ratio from the water into the organic compounds that were synthesized in that water to understand how that plays a role, or which compounds came from where in that process.
Thank you. And again, if you are a member of the media on the telecon line, please press *1 to be put into the queue. All right. All right, I see another question in the queue. We have a question coming in from Marcia Dunn with AP.
Yes, I know you don't like guessing, but I'd really wondering, what's the minimum amount of samples that you would guess that you brought back? Are you
I would say the minimum is 1.5 grams because that's what we've measured.
5 grams. Well, do you think you've achieved the minimum 60 grams at least based on what you've seen, even though you've not measured it?
I don't think we can answer that, Marcia. We want to make the measurement.
Okay.
Okay. Next question is from Alexandra Whitsey from Nature magazine.
Yeah, hi again. I wanted to ask about carbonate. Have you seen carbonate? If so, where and how much is there?
Yes, we have seen carbonate. Some of it was visible in the UV fluorescence image that Danny Glavin showed at the auditorium event here in Houston. We are seeing calcite, which is the calcium-bearing carbonate. We're seeing magnesite, which is the magnesium-bearing one, and brunerite, which has magnesium, iron, and manganese in it. So we're seeing several different species of carbonate. It's very early days, as you know, Alex. We want to make sure this is all based on elemental abundances. We haven't done any structural work. So I probably should walk back the calcite in the sense it could be a polymorph called aragonite. So we will be doing all kinds of crystallographic characterization, transmission electron microscopy, X-ray diffraction. But we do see a wide range of carbonates, similar to what we predicted from the spectral analysis of the surface of Bennu from the OSIRIS data.
And can I just follow up with a completely innocuous question after that? Dante, do you have a favorite rock or grain of dust that you've seen so far?
I do, but it's love at first sight right now. So it's looking at those amazing images from Erica Blumenfeld and her team, which is doing the fantastic photo documentation. And I spent all weekend staring at those images, and I do have a favorite grain. I've already told Francis about it. It looks fragile, friable, so it's delicate, possibly. And it reminds me of the dark black hummocky material. It was, I believe, in my panel D on my graphic is the one that I'm currently enamored with. But of course, you know, you can't have a favorite child, so all of them look amazing, but that one I really want to understand what's going on.
Thanks.
Yep.
Thank you. Next question in the queue is from Leo Enright, Irish TV.
Yeah, thanks. Sorry, I'm not trying to dominate the meeting, but if there's nobody else asking questions, I realize you don't have anybody from the Colorado School of Mining, But this is kind of that sort of a question for, on behalf maybe of the children's children who will be going out to these asteroids. You were at a C group asteroid. Obviously, there's this extraordinary Psyche mission about to go out to an M-type asteroid. Could somebody maybe talk us through, if you were a miner, what of each of these asteroid groups that we visited would be exciting about each one? I'm assuming you would be looking, in your case, more at water than anything else, but I simply don't know.
I'll take a shot at that. I've worked with some asteroid mining startups, and they've all gone bankrupt. So it's a tough business, a tough way to make a living. The problems are it's a huge infrastructure investment and a very long timeline at a high risk if you're ever going to see any kind of economic return on the prospect. But of all the cases that we looked at, the one that was the most compelling was, as you mentioned, mining the water, processing that water into liquid hydrogen and liquid oxygen, and using that to refuel spacecraft to go deeper into the solar system. You know, when we launched OSIRIS-REx, it was 2,100 kilograms of mass, 1,200 kilograms was fuel. So you can imagine a much less capable launch vehicle if you could refuel in orbit. But, and so Bennu would be great for that. We still don't have a number on the 8% water. That's a measurement that's coming. Yugu would also be a good target because it does appear to be very rich in water as well, and then easy to transport, and you could do the dissociation into liquid hydrogen, liquid oxygen down the road. So the sci-fi geek in me can't wait to see this happen. The practical scientist realizes we got a lot of work to do before this is really even credible.
Let me jump in as well. Sure. I'll also point out that we actually had a number of members of our engineering team who are graduates of the Colorado School of Mines. So with respect to them. But when you have an enterprise like this, you need to know what your customer is. And the customer will dictate what it is you need. So if there's a need for, I don't know, a catalytic material for spacecraft in situ, then that's what you'll mine. If it's needed for fuel, that's what you'll mine. So find the customer first and then develop your business plan.
Good advice.
All right, and I think we have Nikki Fox who wants to follow up on that.
Yeah, thanks. I was just going to sort of remind everybody that NASA does not do missions to mine asteroids. We go to study them, to learn about them, and to just gaze in wonder at them and open the treasure trove of discoveries that our asteroid missions discover. And so I was super excited about the samples coming back and being able to look at those, and also getting ready to go Psyche tomorrow.
Hear, hear.
All right, the next question in the queue is from Kenneth Chang with the New York Times.
Hi, thanks for taking another question. I was wondering if you could compare what you saw in the quick look research versus what you had seen in the remote measurements when you were at Bennu. Did you see hydrated clays then? And I guess what sort of confirms what you saw previously and what was actually new? Thanks.
Yeah, thanks, Kenneth. So the predictions were very specific. We thought we would see from both two instruments, the OSIRIS instrument, which is the visible and infrared spectrometer, and the OTIS instrument, which is the thermal emission spectrometer. We did see strong indication of hydrated clay minerals, both in the 2.7 micron region in OSIRIS data and the 10 micron region in OTIS data. We did see magnetite, which is the iron oxide. We did see carbonates, including multiple variations, calcite, magnesite, dolomite, brunerite were all predicted. And we're starting to see that diversity in the carbonate mineralogy right now. And of course, abundant organics all across the surface of the asteroid, which initial analyses support that as well. The species we didn't see that I reported on today were the iron sulfides. And that's because they're not spectrally active. So I had postulated that they would be there just based on knowledge of solar system chemistry, and in fact they were there. So pretty much we predicted the mineralogy very accurately, and we also predicted a very low abundance of anhydrous silicates, things like olivines and pyroxenes, which, for example, make up the mantle of the Earth and a lot of the stony type of asteroids and meteorites. And we have maybe found a couple small grains of those, but they're very minor components, again, consistent with our spectral analysis.
All right.
And maybe I should mention for Kenneth, if you're really interested in the details, I did post the entire sample analysis plan on archive.org for anybody to download and review in detail. Just caveat emptor, it's about 270 pages long.
Our next question is coming from Colin Baker with Al Jazeera English.
Hi, thanks for taking my question. So with Hayabusa and with Stardust, the public perception at the end was all about amino acids, and I just want to know, and forgive me if you've already explained this, what's the viable path from where you are right now to learning about some of those much more complex forms of carbon? How long do we have to wait? How many steps do you have to go through to get there? What are you expecting to find?
So I can take part of that. Is we have a detailed sample analysis plan that you can also look at on archive, studying the organic materials from the volatiles all the way up through the large compounds, the pHs, the insoluble organics, with an emphasis, of course, on soluble compounds relevant to astrobiology, to life, amino acids, small peptides, sugars, all these sorts of compounds. Once the samples have been decided upon and allocated to the team, then the worldwide organic sample analysis team will get to work and have those results soon. And I'll let Francis tell us when that might be happening, but we have to do whatever's best for the sample.
Yep. So we anticipate getting more sample out to the science team within the next month or so. And the general scientific community will have a shot at these samples when the sample catalog comes out in about 6 months from now.
Next question is from Linda Shiner, Smithsonian Magazine.
Hi, I have a question about sample distribution. You mentioned that some of the sample from outside the TAG SAM was already sent to Goddard and to Carnegie. What was the purpose of that distribution, and what type of analysis was done?
Yeah, so part of the plan was always that there was going to be this quick look analysis with any material that might be on the avionics deck and outside the TAG SAM. We actually had even more than we were anticipating, and so we sent 138 milligrams out to that team so that they could do those preliminary analyses. We've containerized about 1.5 grams of material so far just from the avionics deck, and the material we saw today on top of the Mylar flap, we haven't even measured the mass of that material left, so we've got a bounty of material here. And I'll let Dante tell you a little bit about what they were able to do with that 138 milligrams.
Right. Thank you, Francis. So I mentioned when Kenneth Chang had the question, we had these predictions about the nature of the sample based on the remote sensing campaign at Asteroid Bennu, and we wrote a 270-page sample analysis plan based on those assumptions. So the very first thing I wanted to know was my sample analysis plan still valid, or did I have to scrap the whole thing and start from scratch because Bennu surprised us once again? So the good news coming out of this is we're pretty much seeing what we expected. In some cases, we're surprised, but in a very good way, the high abundance of carbon being, I think, the prime example of that very wonderful surprise. So I can rest easy that we will continue to work through the sample analysis plan as envisioned. It is a hypothesis-driven plan, and the hypothesis number one is testing the prediction of the mineralogy and the abundances and the relationship to known meteorites. And so I feel good that we're going to be able to continue down that path. Of course, we did collect a biased sample. The stuff that was outside of TAG SAM was very fine-grained, probably why it got out. And there's much more coarse particles and large particles on top of the Mylar flap and inside TAG SAM, and we don't know what they're going to be like. But part of our plan is to assess the diversity of material, and any new kind of rock that we see, there is a plan to go ahead and do basic characterization and see how that ties into our hypothesis-driven sample analysis plan.
Next question is from Assam Ahmed from AFP.
Hi, yeah, thanks for taking my question. A couple of things, one a bit on the scientific side and one a bit more on the engineering. The first one is, what is sort of the competing theory for how Earth acquired its water and carbon? If the dominant is that it was seeded from asteroids? What is the competing? And the second question was, sorry to harp on about this, but with the TAG SAM, I think Dante mentioned at the top of the call that some of the material slipped out of the Mylar flap. Does that mean that there could be less than the 250 grams, which was estimated? And when will we know? I mean, is it possible that most of that material is no longer there? Thank you.
So there are a number of hypotheses on Earth's water, from depending on the amount of water in the deep mantle of the Earth, how much of it could have come from initial accretion, to how much water was delivered from extraterrestrial materials such as comets and asteroids and the ratio of those materials. It tells us something about the stratification of water isotopically within the early solar system. So these are hypotheses that we can investigate, and every exomaterial we look at gets us a little closer to understanding this diversity of origins of water and volatiles on the primitive Earth. Let's see, the other one was on the
mass, the TAG SAM leakage. I'll take
right.
that.
Okay.
Yeah, so it's important to recognize that, prior to understanding that material was leaking out of TAG SAM, we had a very elegant physics experiment plan to measure the mass of the return sample. We were going to take TAG SAM and extend it out 90 degrees from its sample collection configuration and kind of twirl it around. We did that when the TAG SAM was empty. We were going to do it again when the TAG SAM was full, but once we saw the leakage, we realized that would just exacerbate the problem, and we'd probably lose more material by trying to make the mass measurement. So the guidance, navigation, and control team at Lockheed Martin came up with this new technique using the momentum transfer between the robotic arm and a component on the spacecraft called reaction wheels, which absorb momentum, basically. And so we have 250 grams, but I want to make sure people understand there's an uncertainty on that of 101 grams. So even within that measurement, if we had 149 grams, it would still be consistent with the estimate, as well as up to 351 grams. So if we're anywhere in that range, then the GNC team did a fantastic job of estimating our mass. And nobody is more anxious than I am to get that mass number, but I'm practicing my patience, and I'm fully respectful of the need to do this carefully, because it's not just about the science program on OSIRIS-REx, it's about the future integrity of the entire collection. And we're dedicated to making that happen, and we will get that mass number to you soon. So I urge patience as I'm practicing it right now.
Thank you. And I will remind those on the line, if you have a question, please press *1 to join the queue. Next up, we have a question from Jeff Parrott, who is called in from the Salt Lake Tribune.
Hi, good afternoon. Cheers from Utah. Just a quick question about kind of looking forward to that Apex mission, what you're seeing and what, you'll decide on what you've seen in the next few weeks. Will that shape that visual-centric Apex mission? Will it help those OCAMs understand what they're looking at a little better? Kind of how does it shape this follow-on mission in the future?
That's a great question. And yeah, one of the key objectives of OSIRIS-REx is the spectral interpretation, right? We wanted to understand how well the instruments that are on board the spacecraft did at predicting the composition of the material on the asteroid surface. And by bringing some of that sample here to Johnson Space Center and ultimately distributing it around the Earth, so far we're validating those instruments. They really look like they performed well. Their sensitivity was as we expected, in fact exceeded it by a bit. And so we can then confidently go and take that same suite of instruments with better calibrations because of the return sample and do an even better job characterizing asteroid Apophis, which will be very different. We're expecting it not to have these hydrated clay minerals and these carbonates, but to be stony and metallic material like the most common type of meteorites that land on Earth, what we call the ordinary chondrites. But yeah, this was about ground truthing our astronomical data as well as our spacecraft-based data, and the samples, a lot of our sample analysis plan is focused around understanding how well those instruments are capable of characterizing the surface. So far it looks really good, and that gives us a lot of confidence going into the Apex extended mission.
Thank you.
Next question. Thank you. The next question we have is coming in from Matthew Perot with La Presse.
Hi, thank you for taking my question. I know you asked us to be patient, but do you think you'll have a number on the weight of the sample before Christmas?
Absolutely. I'll let Francis answer that one. Yeah, but I hope so. I don't know if I can wait that long.
Yeah, we should have a mass by Christmas for sure. I'm expecting one within the next few weeks.
And so am I. Yep. So, yeah.
Excellent, thanks.
Yeah, and just to add, the only reason we don't have one now is because we found a lot more asteroid material on our way in than we were expecting, and that's a great problem to have. And so we're containerizing that material as carefully as we can, documenting everything in the process. And like I said before, we are very excited about the volume of material we see, and we can't wait to convert that volume into a density and provide you with a mass.
Thank you. Next caller is Colin Baker with Al Jazeera English.
Hi. So I know there's this long-term plan to store some of these samples, or actually quite a large amount of the samples for future generations to study. Is there like a time capsule timeline for how it's opened up over time, how it's stored, when scientists of the next generation are going to have access to it? Do you have like a roadmap for that?
Yes, what we have for every single one of our astromaterials collections is what we call a conservation plan. And this conservation plan gives us a sort of target to aim for how much of the sample to distribute every year as we go forward. And that conservation plan is designed to keep abundant material for this collection for decades and decades. And so there's not going to be any sort of putting stuff away and leaving it there, and that is the specific sample that will not get touched. It's just our overall conservation strategy for how we do astromaterials curation, so that there's always going to be material available. We're always going to be answering questions as they come up, using whatever the technology available is, and we conserve it so that it's there for good. We don't have time to go.
Thank you. And there are no more questions in the queue. If you do have a question, please press *1 to join the queue. And if not, I'll go around the room and ask the folks in the room if they have any words or things that maybe they think you guys didn't ask.
So it's truly exciting to be here after waiting for 19 years to get a sample from an asteroid to study. Waiting an extra couple weeks for a wait is hard, but knowing that we're doing everything that we can, and that curation is doing everything that they can to maximize the value of the sample for the future is worth the wait. Taking the time to containerize and secure every little bit of sample that will hold future discoveries is worth the inconvenience right now.
And I'll just say, watching the curators working in the clean lab with their hands on the glove box, it's so impressive. They are so steady. They are so well rehearsed, and this collection is in great hands. I couldn't be more proud of the entire team.
Yeah, I definitely want to second that. It's been an amazing experience to be here at Johnson Space Center. And even though we want to know the mass, every day there's been something new that's been revealed about the nature of the collection, either from continued work on the quick look sample or flipping over TAG SAM and seeing those particles exposed. So we're not bored. We're having a great time, and I treasure these moments, and I know I'm rapidly running out of them, but where the team comes together with a focus like we have right now, and everybody's working towards the same goal. The excitement is palpable. Spirits are high. It's quite a wonderful time to be engaged on this program. And so I'm not begrudging the delicate and painstaking process we're going through. I'm reveling in it. I'm enjoying it. And I know the mission, there's 2 more years left in the sample analysis program after working 20 years on something that doesn't seem like that long of a time. So it's a little bittersweet to think the end game playing out, and also heartening to know that it's just establishing a baseline for future generations that'll build on our knowledge, that'll be smarter than we are with better equipment, hopefully better funding, and do a great job with this material collection well into the future after all of us have moved on.
All right, and I'll toss it over to Nikki Fox. I know she has some closing words she'd like to say.
Oh, hi. Yeah, thanks so much. I just actually want to take a moment to just give a major shout out to this incredible team. There was nothing about OSIRIS-REx that was easy. Perfect launch, but, they got to Bennu. It was not what they thought it was going to be. It looked so different. They had to come up with really, really creative ways to actually survey the asteroid, to find that perfect place to go down and do that tag maneuver, bring back the samples. It's just been just such a success, but they are just such a wonderful team. And given that the team is kind of splitting, and some are staying with the samples and some are going to Apex, I think this is just a really great moment for us to show them a lot of love for an incredible job. Really, really, really well done. I'm okay to wait another couple of weeks to know how much sample we have. I can't wait to actually come out to Johnson myself and get a chance to see those samples. But just an incredible, incredible job to an amazing team. So on behalf of NASA, thank you, OSIRIS-REx.
Thank you, Nikki.
Thank you. And that concludes today's Media Telecon. Thank you to everyone who dialed in today. I'd also like to thank the panelists and to our operator, Dustin, for their time.
That concludes today's conference. Thank you for participating. You may disconnect at this time.